let's get going.
Okay,
George,
I
a brief
apologize.
introduction. A brief introduction.
Okay, very brief introduction. Right. Well, our guest today for the 14th talk in the OSMU series is George Sparling, for who my interaction with whom goes back over a span of 50 years. And I was just in the middle of saying that I recall when he gave a very interesting and very penetrating talk on twister theory to an audience at King's College London in 1975. In fact, one of the things which got me so excited and interested in twister theory that I started going to Roger's seminar on that topic in Oxford. And it's one of the things which led to the creation of the Archive Trust. So I just wanted to mention that. He's going to talk to us today. His title is Space-Time is Six-Dimensional and the two extra dimensions are time-like. So over to you, George.
Okay, so let's go. Space-time six-dimensional, okay. Extra dimensions are time-like. So what this is about is basically the idea of stuff that I know that people here are very interested in, and that's the idea of octonians and things related to octonians. But the six-dimensionality comes from the idea that the correct octonians that one wants are actually split octonians, whose symmetry group is 4-4, and the associated, unlike ordinary octonians, but as soon as you have signature 4-4, you have the idea of null octonians, and the projective space of null octonians is six-dimensional. And so the idea is that underlying twister theory, and this is really basic twister theory, underlying basic twister theory are the split octonians. And I think Roger may have talked something about this, I'm not sure. So the thesis is, whether it's tenable or not is unclear, but the thesis is that at some point in the universe's history, this structure played a role. So perhaps a primordial structure, which in order to get to ordinary ideas of space and time, required symmetry breaking. So what I'm going to start out today with is just talking about the whole theory of octonians, because I know it's of interest to at least some people in the audience, particularly our host. But I'll do it in the spirit of Roger, as you'll see very quickly, and go from there to talk about other things. If I have a chance, I'll write them on the screen, but depending on whether things can be fixed by the end of my talk. Otherwise, I'll just mention it in passing. Okay, so let me show you some pictures, which some of these are things I've shown before to some people in the audience. This is one of the basic ingredients of twister theory, what's called the Klein quadric. I'm just going to show you pictures at the moment. I'm not going to worry about formulas. We'll come back to it later. The Klein quadric is a four-dimensional gadget, and it's ruled by these lines, and it has in it planes. The planes are actually what are called twister planes, and then there's another kind of plane, the dual twister plane. A lot of people will know all this stuff, so I just want to show you pictures for the moment. Twister hyperquadric looks like this. This is a rough picture of the what's called projective twister space. And the important point is a bit in the middle, which is the null twisters, and the stuff on each side. This is a picture I just happened upon. Jorg, I was recently in Cambridge, invited by Maciek to give a talk there, and Jorg was there, and some of what I'm going to say today, if I have a chance, is relevant or was inspired by his talk, so I thought it was good to leave it in there. Then some of my family writes stuff which is vaguely relevant. One of the things about twistor theory is that it's basically tilting at windmills, because there's no clear idea of what the theory is ultimately. And certainly recently in my own work, I've made some rather surprising progress, which has certainly turned things upside down to some extent. If I have a chance, I'll talk about that later. In honor of Roger, there's a picture that is in some obscure building in Seattle. There's 2 pictures of Roger's tri-bars. Which just happened to be found. Okay, so now let's get down to business. Galileo says,
press this, and then at the bottom it says share, and you press share, and then you can use that.
Okay.
Not until you.
Okay. So according to Galileo, symmetry is important. He talked about physics in a moving boat. Okay, now let's get on to some formulas. So I'm just going to introduce the ideas of twistor theory in case somebody in the audience has never heard of it. The theory is based on complex numbers. That's the first thing. And initially a complex 4-dimensional vector space. And the key idea is that it has a Hermitian form on it, which is signature 2-2. So that's going to lead us directly into octonions. Oh, by the way, I should have said, if anybody wants to interrupt and ask questions, I'd be very happy. Otherwise, my talk may be a little dry. So anyway, you have a complex vector space with signature 2-2. So the symmetry group is naturally U2-2. Now, all this was discovered by Roger, of course. Because it has signature 2-2, you can talk about null twistors such that the signature Z.Z bar is 0. Projective twistors are 1-dimensional subspaces. The symmetry group is U2-2. And it's a basic fact that its subgroup SU22, which has dimension 15, is the spin group for SO24. Now, how do you get Minkowski space out of twistor space? Well, it turns out that it's just the space of totally null, complex 2-dimensional subspaces of T. That was what one of the earlier pictures was supposed to represent. But there's a little bit more to than that. Of course, Minkowski space has a conformal structure, and so you need to know the conformal structure, but it's very simple. The conformal structure is such that 2 points are null related if the intersection of the 2-dimensional subspaces, which would normally be 0, if the intersection is non-zero. And it turns out that if they are null related, there's a unique null projective twistor in common, and that means that the projective null twistors actually give you null geodesics in compactified Minkowski space. So that's the geometry. And then there's a key fact, and that is that there's analysis that goes with it. And that is that massless spinor fields can be described in terms of sheaf cohomology. I wonder if this is the point at which I could test. According to my wife, things are now hooked up.
Please go ahead. Go ahead.
Let's see if I can write something. Pam, are you there? Touch what?
Screen, and
Yeah.
then share comes up at the bottom.
Share.
See it?
Right.
Now you can write.
Share what? Whiteboard?
Share
Yeah.
iPad. iPad is.
Can you guys see?
Yes,
you guys,
yes.
you can see
Now
it.
write on it, please.
Well, I can't see it.
We can see your whiteboard, George.
You can?
Yes.
I can't see it myself. Okay, let's see what happens if I write. Okay, so the key formula is that of Bateman.
Yeah, it's working. It's working.
Yes, it's working.
You
fine.
can see that?
Yes.
Okay. And I'm not sure if it's really Bateman or Roger's version of Bateman. I was unable to find it in the literature. And what it is, now it's not working. What's happened? It stopped working. Why?
Does your pencil have charge?
Oh yes, it's charged.
Yes, it's working now.
Okay. Okay. So here's a formula, which you may have seen before, something like this. Hopefully, I'll get it right. So there's one formula. Okay. So here you're doing a contour integral, and you have 4 variables, u, v, z, and z bar, which are the space-time variables. And so when you do the integral, you get a function. And the function is a function of u, v, z, z and z bar. And according to Bateman and Roger, it obeys the Laplacian equation, which is the wave equation in this case. Okay, and it's easily checked. You just do partial derivatives, and it just drops out in a split second. Okay, a slightly improved version, which is I'm pretty sure due to Roger. A slightly improved formula is this one. This formula. Okay, so the point here is that one has made the complex variable lambda, which appeared there, we've made it projective. So everything only now depends on the ratio of lambda to mu. And now, in order for this to make sense, this function must be homogeneous to degree -2 in lambda and mu, or in the twister. So you think of this as a function -2 of the twister z, these being the 4 components of the twister. So given a function on the twister, you can extract from it a function of space-time here. So I'll call that just 5x, x being labeling the 4 points u, v, z, and z bar. And if you have a -2 function, this is then a scalar. And then if you put in some powers of mu and lambda, you do the same thing. Whoa. Now I've lost. Okay. You do the same thing here. I won't rewrite it. Put in some powers of lambda and mu, you get something that's got indices depending on r and s. These are integer powers. And now you can put in a -k -2 there. And in order for everything to balance, r plus s must be k. And so you get a bunch of fields here labeled by these integers r and s. And this, in the end, can be shown to describe spinor massless fields. Okay, now there's an important innovation here. I mean, I've only just realized I've been stewing on this for like 60 years or 50 years at least. I've only just realized, although I knew about this many moons ago, how important this is. And that is, there's a simple modification of this. So we write exactly the same formula. Yeah, sorry. Okay, but now it's a double integral, and we do d lambda d mu. Okay, notice the difference here. In the original one here, you're using a projective integral here, and you have a specific homogeneity. If you put a different homogeneity in there, you would actually get 0 for this particular integral. But if you put a different homogeneity in and put in suitable compensating powers of lambda and mu, you do get a field, and that gives you your massless spinor field. Okay, but suppose you want to do a combination of spins. Okay, then this is the answer here. Okay, now of course I've known about this for a long time, but this is actually a key ingredient in what I want to say later on, perhaps if I get a chance. Okay, so notice in this case you do not have to specify the spin at all, and if it happens that F is homogeneous of a particular degree, then you can effectively integrate out and get the original fields that one had here, depending on the various spins, because you can just scale out the non-projective part. Okay, so contemplate this a bit, and now I'll return to the octonions if I can. How do I get out of here? These.
Just go back to share and choose your slides.
Share. Or should I say stop? No. Share on my screen.
Do you see share downstairs? You should select your PDF file. Your slides are open on the screen now.
Yes.
So you have to select that window. It will be showing up on the share screen.
Okay. Sorry about my incompetence here. Let's. Oh, here it is. No, that's the text file. Where's the PDF file? Here, maybe. Yeah.
Oh, great. Yes.
So that's the bottom line, is that you can get spinor fields in a natural way out of twistor theory, and they are massless spinor fields, and you can get arbitrary spin. Okay, let's go back now to the first main topic of the talk, which is triality. Okay, now a lot of people are presumably familiar with this, but I want to reprise it, and I expect at least some of what I'm going to say is not familiar. So if this is too silly, just stop me, because I've got plenty of other stuff to say. So triality is a relation between three vector spaces. In the end, they'll all be the same dimension, so you have an element which I call Tor, standing for triality, which acts on each of the three vectors. So trilinear form. You can use it to get out of it bilinear forms with values in either one or the other space. So the Tor YZ that I have at the bottom of the page here is understood to be in X, and Tor ZX is in Y, and Tor XY is in Z, and so on. To be very concrete, here is a formula for triality in 8 dimensions. Okay, so you just write it down. How you get to it is another question, but it's just some messy formula. And its most only obvious feature is that it's trilinear. But it turns out that if you differentiate appropriately, it obeys simple differential relations, namely that if you differentiate with respect to either x, y, or z, the resulting thing dotted with, if I differentiate with respect to x and dot it with itself, I get the product of the quadratic forms on the y and z space. Okay, so that's one version of triality. This is the theory that underlines octonions. The second version it underlies split octonions, and that is the 4-4 triality. So you just write that down. It looks exactly the same as the previous one, but if you look through it carefully, you'll see that there's some sign changes, which correspond basically, if you want to relate one to the other, you're placing some x's by I times x's, that kind of thing. So you can get from one to the other. Or another way of saying it is, if you complexified the setup, it would be identical. And again, you have the corresponding differential relations. Here, the metric is now a 4-4 signature metric. So we have a 4-4 metric here, and otherwise it looks exactly the same as the standard triality. Now, where do these formulas come from? They're actually a part of the representation theory of the Clifford algebra of the orthogonal groups. And so effectively, because the spin representations are effectively unique, these formulas are also effectively unique. Okay. Now, this is where I want to go to mention that you can get triality in a completely abstract way. And so that means, in particular, you don't have to necessarily think of yourself as being in the context of vector spaces. It could be some other context, in particular, what's called symmetric monoidal categories. So then defining relation is written in a funny way. I'll write it better in a second. But anyway, it's done in such a way that you eliminate all the references to the Y's and Z's that we had before. So you just abstract them away. And as a technical thing, I assume that the tensors, the X, Y, and Z tensors are independent of each other. So we will relate X tensor Y and Y tensor X are thought of as the same. And as soon as you do that, you're allowed to write everything diagrammatically. So there's a long tradition of diagrammatical approaches to tensors, culminating in Rogers' famous paper on negative dimensional tensors. Because of the, we're actually not going to use negative dimensional things today. Because of that, we can do everything diagrammatically. And the three tensor types, I'm going to just use colors to distinguish them. So we've got three colors, and for every formula that I write using one particular color, there'll be a corresponding formula in the other colors. So here's the metric, for example. So this is in magenta, but there would be a yellow metric obeying the same relations. And the dimension for this is going to be the same for all three. This is what the triality operator looks like. If anybody doesn't understand what's going on, just ask me, okay? So here's a picture of the triality operator. So you think of it as acting on vectors. The vectors would be attached. If it was, say, a yellow vector, you'd put it on the yellow end, or a blue vector on the blue end, or a red vector on the red end. But the point is that you don't need the actual vectors themselves. Here's the Clifford algebra identity. This is basically the commutator of two elements is a multiple of the metric. So this is the key identity. And remember that there's three such identities because you can commute the colors. I'm heading towards a theorem, and you might very easily guess what the theorem is if you're an expert in this area. So let me show you a little bit of how you actually prove the theorem. So you write the triality relations slightly differently, thinking of it as a symmetric bit and a skew bit. The symmetric bit is given by the previous slide. So that's the first term in the relation on this page. And then there's a skew bit. The skew bit is going to be the key ingredient. So now you can start playing with these diagrams. So here's a beautiful little formula. If you have a triangle like this, it turns out to be proportional to the triangularity operator itself, where you collapse a triangle to a point. Now it turns out that what the key thing is to understand what happens when you glue triangulities together in bunches.
Sorry, George, are you still writing formulae? I can't see any formulae.
No, I'm not writing. I'm on my. Oh, I wish you'd interrupted me before.
No, maybe it's just me. Can people see George's slides?
Yes, yes, yes.
Oh dear, I can't.
I
Don't worry.
see the slide very clearly.
What can you see, Marty?
I can just see you, but don't worry about me. I'll figure something out.
You can just see me. Oh no. That's awful. But how can that be? Anybody?
I think the Zoom update is doing strange things these days. In a previous talk also we had issues.
Well, I don't know what to do about it.
No, I think you should go ahead.
Okay. Well, Maciek, I can send you the slides so that you can see them. Otherwise, you're going to have to imagine them.
That'll be great. I'll imagine everything. Don't worry.
Anyway, okay. So I hope that. Anyway, you glue triangulities together in boxes, and you prove various relations. So I don't want to dwell on them too much. But eventually you can show that on this page, for those who can see, I've looked at 4 triangulities glued together in 2 different ways. We show that they're related to each other, apart from things involving the Kronecker delta. And notice as you do so that terms involving the dimension n come in. And now we get to the main point. Taking skew parts, you get a formula for the sum of 2 double box things glued together. And it'll turn out that we can actually get a formula for the difference. Again, we start with 2 copies of the basic triangularity, glue them together, and you get some relations. Again, you can look at the slides and see how all these relations you can actually deduce directly on the screen if you spend a bit of time fiddling around with symmetries and whatnot. So in the end, you get a formula for what are called the off-diagonal double box, where you have 2 inputs that are red and 2 inputs a different color. And what you find that when you iterate them, again, you can delete the interior at a cost of a factor of n minus 4. And so it turns out that if you, so this is where in the previous one, we have 2 inputs that are red and 2 outputs that are yellow. We can also have a formula involving 2 inputs that are red and outputs that are red, the same color. And what you find is that as long as you multiply by a factor of n minus 4, that the 2 inputs that are red for the double box agree when the interior lines are blue, they agree with where the interior lines are yellow. And previously we had a formula for the sum of the 2, and therefore since the 2 agree, you can just say that this quantity is equal to half the formula for the previous sum. And so you get an expression for the double box with all n's the same color as just proportional to the Kronecker delta. And then there's what's called a triality preservation formula, which I won't dwell on at the moment. It can be proved. I don't think I'll take the time to do this. But now we get the famous theorem of Diophantus of Alexandria, Brahmagupta, Euler, Dagan, and Adolf Hurwitz. All of these people were involved in working with things like sums of squares and relations, such as, for example, the ones that come up in complex number theory, where you have the length of z times the length of w is the same as the length of z times w, that kind of formula. So that's basically an underlying feature of triality. The theorem is that if you work over a field not of characteristic 2, because it's at various points I used that I could divide by 2, if a triality exists, then the dimension must obey a polynomial relation, which is n squared times m minus 1 times m minus 2 times m minus 4 times m minus 8 must be 0. Okay? So if you're working in the context of, say, real or complex numbers, that means the only possibilities are that n can be 0, 1, 2, 4, or 8, and those correspond to things like quaternions, octonions, complex numbers, reals, and n equals 0 is just sort of trivial. And so you can just write down the proof just straightforwardly using the ingredients that we have. You look at 4 boxes, 4 double boxes glued together, and first you can show that you can reduce, as long as notice you have to multiply by these factors of m minus 4. As long as you multiply by m minus 4, you get a simplification of the 4 boxes down to 2 boxes. On the one hand, this guy can be simplified using the first term on the left-hand side here can be simplified using properties of the input 2 reds and output 2 reds, and that simplifies to the left-hand side of this equation here, 2n squared times m minus 4 times the skew symmetrizer. And you do the same thing for this other side here, and you get a factor of n minus 4 cubed times n times the skew symmetrizer. So you get this relation just coming out of nowhere, basically, and all you do is you collect terms, and that's the answer. So it's somehow a deep fact, and yet in some sense, the proof is really quite straightforward. But notice that I nowhere used elements at all. I just used just properties. I did use there's a trace, but apart from that, that's all that was required. So we're done. I'm running out of time, so I'll just mention very quickly how you build from trialities to Jordan algebras. Jordan algebras, again, a lot of people in the audience will already know all this. For Jordan algebras, you form a symmetric matrix whose entries down the diagonal are numbers, and on the off diagonal you put one element of each vector space. And then the Jordan multiplication is basically matrix multiplication, where you throw in the triality at appropriate points. In the case of dimension 8, which is octonions, this algebra has dimension 27. From the Jordan algebra, I'm just recapping basic structure that is developed over the years. From the Jordan algebra, you can get the phase space of Freudenthal. For some reason, you have to throw in an extra 2 dimensions. So you take essentially the cotangent bundle of the Jordan algebra, which would be 54-dimensional, but you need an extra 2 dimensions in order for everything to work out appropriately when you work out the group structure. So you end up with a 56-dimensional space built out of the Jordan algebra. And it turns out that on that space, you can define a Lie algebra consisting of Hamiltonians, quadratic Hamiltonians, and those Hamiltonians form a vector space of dimension 133, and they close under the Poisson bracket to give you the non-compact real form of the exceptional complex Lie algebra. An interesting...
Sorry, could I ask you a question?
Yeah, definitely.
Yeah, this is very interesting. I did not know of Freudenthal's phase space.
Okay.
Does it play some role in classical mechanics if you're using, say, octonions? And because you have E7 here. So E7 is the symmetry group associated with the entire phase space.
Yes, including the extra 2 dimensions. If you leave those dimensions out, it doesn't quite work.
Okay.
So I've no explanation. I mean, this is not my idea. I have no explanation of why you need the extra 2 dimensions, but it's a standard fact.
And so, but does this play a role in physics somewhere, the Freudenthal phase space?
Well, other people may be more familiar with this, but it turns, if you think about quantizing this, you end up with a space of dimension 57, and that's associated with the exceptional Lie group E8, and it appears it appears in supersymmetry.
Yeah, this is very interesting. Thank you.
Okay, so I just want to mention quickly how you get to these exceptional Lie algebras. You consider 2 trialities, okay, instead of 1. You have 2 sets of generators which correspond 1 to each triality. So you have 2 orthogonal groups, which in this picture are represented by skew tensors, and 3 sets of tensor generators. If you want to count dimensions, suppose you're in 8 dimensions, the 3 skew tensors are each give you a Lie algebra of dimension 28. But if you're in 8 dimensions, the constraint of preservation of the triality actually reduces, gets rid of 2 of those. You can determine 2 of them in terms of the other one. So the blue and green one would be determined in terms of the magenta, whatnot. So you have 28 dimensions for the magenta one, the upper magenta one, another 28 for the dimension of the lower one, and then 3 sets of tensor generators. They're made from tensor products of upper and lower. Each one of them is 64 because it's 8 times 8. So they give you 192. And then you add the two 28s, that gives you 192 plus 56. That gives you 248. You have all kinds of relations, which are very...
248 is the dimension of E8.
That's right. And you write down the Lie algebra, and eventually you prove that it closes as a Lie algebra, and that gives you there's all kinds of things going on here. That gives you the Lie algebra of E8, as you were saying.
George, can I just come in to say, please don't feel under any compulsion to hurry the presentation. We don't have a strict rule. You've only been speaking for less than 45 minutes. You have the full hour, but if you need to go over time, there's no problem.
Okay, well, I am getting. I've basically covered what I consider the stuff that was of most interest to our host and at least some of the other people in the audience. The end result is that as you vary the trialities, you not only get E8, which was that maximum one of dimension 248, but you get all the various Lie algebras of what's called the Freudenthal magic square. So I'm sure this is known in some sense. I'm not claiming this is a theorem. But again, it's very nicely organized in terms of the Penrose tensor diagrams. That's about it. Now, the question is, okay, so the claim is that there's some connection between triality and reality. Okay, so we want a path to twistor theory. Well, that's really quite straightforward. You want to start at 044 and end up in U22. Okay, well, that's easy. What you do is you pick one of your, I should mention, before I do that, I should mention how you get from triality to octonions. In octonions, if you are familiar, the symmetry group's really G2. How do you get that? Well, you actually pick a unit vector in one vector space, a unit vector in another vector space, and then the third unit vector is the product of the Tor product of the triality product of those two vectors, and that gives you a unit vector in the third space. So you have three unit vectors, one in each space, and the structure of octonions is got by using those three vectors to convert all the three vector spaces into one. And then you can deduce the multiplication theory of either split octonions or the octonions from that. So you get to octonions by fixing vectors, one in each vector space, ultimately. That's not how you get to twistor theory, at least not directly. And in fact, twistor theory is not quite, it doesn't quite agree with octonions from that point of view, even split octonions, because that would require, it's okay to specify a particular vector in one vector space, as we'll see, but you can't do so for the other two, as we'll see, or at least it doesn't seem reasonable to do so. So how do you get to twistors? Well, you focus actually just on one vector space, and instead of picking a single vector, you pick two. So you pick a two-dimensional subspace of one of the vector spaces. In retrospect, it's kind of obvious that one should do that, such that we're in 4-4 signature, so you just choose that the metric be positive definite, let's say, in the 4-4 signature. That breaks the symmetry of that particular space down to O2 times O24. Once you've got a two-dimensional subspace of that space, its orthogonal complement, which is 6 dimensions, naturally carries a structure of O24, and the null cone of the orthogonal complement can be thought of as the compactified Minkowski space. So as soon as you specify this two-dimensional subspace, you end up with a Minkowski spacetime. Okay, but now we've got the other two spaces to worry about. And so what you do with those is you pick any two elements of the space J in the space X and take their product, and their product, each one gives you when you apply the triality, gives you if you fix one element, you can use the triality to map you, using that element, to map you from, say, the Y space to the Z space. But if you've got two trialities, you go from Y to Z and then back from Z to Y. And so what you get when you take the composition of the two trialities is an endomorphism from one vector space Y to itself, or from the other one to itself. So you get two endomorphisms. And if you just play with those endomorphisms, you immediately find that you end up with basically a complex structure. If you pick two, everything is invariant under linear combinations of the basic elements that you choose, the J and K. So you might as well end up with a orthonormal frame. If you choose an orthonormal frame, then the corresponding endomorphism has square minus 1. and that gives you the complex structure of the space Y. So in other words, once you specified a two-dimensional subspace of the X space, there's automatically a complex structure organized for the for the Y space, and similarly a complex structure for the Z space. Then if you understand that, okay, we don't just have Y and Z, but we also have the triality relating them. So you can look at the pairing between the Y and the Z space, where using the triality, you throw in an element for the third entry of the triality, you throw in an element of the space J, the two-dimensional space J. So you think of this as giving Y and Z, you basically get an element of the dual space of J, but J is a two-dimensional space, so you end up with a map from the pair Y cross Z to a two-dimensional space. But the J space has a natural complex structure, so you're actually mapping from Y cross Z to the complex numbers, okay? But it turns out it's not really the complex numbers. It's the complex numbers, but with no preferred real part. So unless you break the symmetry in the J space, there's simply no preferred real part. So what that means is you end up with a twistor space, let's say Y, and a dual twistor space Z, but they're only weakly dual in the sense that it makes sense to say that Y dot Z bar is 0, but it doesn't necessarily make sense to say that Y dot Z bar is a complex number. It's an element of this vector space, but it's not actually a complex number itself. It's an element of two-dimensional vector space with a complex structure, which is a curious thing that I only just realized as I was writing this up. If you actually wanted a complete duality between the two twistor spaces, you would actually need to break the symmetry down of the J space down into, you'd have to prefer a particular one-dimensional subspace of the J space to do it. So that would correspond to an intermediate symmetry breaking from 044 to 034, and then down to the 024. Finally, once you've got down to 024, you can break down to de Sitter or anti-de Sitter or a Poincaré by choosing an appropriate extra symmetry breaking. So I think I've made a fairly solid case that triality is relevant to twistor theory, and that one should in fact take this triality seriously. How it fits in with physics is not entirely clear, but certainly there's some promise there. And one of the things, a lot of this triality stuff I discovered in collaboration with my former student, Phil, and Phil Tillman, and the more recent stuff to do with the theorem I presented and what I'm about to say now is more in connection with my current collaborator, Jonathan Holland, who we work with. Everything that I've said today is based on work with Jonathan. In particular, just like in twistor theory, there's analysis that goes with this. Remember, there's contra-integrals. Well,
sorry, could I interrupt you if you don't mind?
Yeah.
So as you said, triality seems very relevant to twistor spaces, twistor theory. At this stage, already is a 6-dimensional spacetime implicit in some sense. I remember from Basil Hiley's talk earlier in this series saying that 6D spacetime is a more natural home for twistors, and 4D spacetime is gotten as a projection. I may be wrong here, but we are yet to get.
I'm not sure exactly what was said there. My point of view is that there is a theory here. I'm not sure what else one says. There's clearly a very strong relation between the whole concept of triality and split octonions and twistor theory.
Yeah, can we add 6D spacetime to that? No.
Well, yes, because of what I was about to say. The analysis involves, just like in twistor theory, you start with one space, do an integral, and you end up in another space. Well, what are the spaces? The spaces are the null spaces of each space. So if you start out with a function, say in the null space of X, so that's a remember, X is an 8-dimensional vector space. The null space is 7-dimensional. The projective version of that is 6-dimensional. So you start out with a thing in a 6-dimensional thing, do an integral, and you end up with something in one of the other spaces. So in fact, you can go both ways. You can go from X to Y and X to Z. And so you end up with a triangle of transformations from X to Y to Z, and Z back to X. Just like in twistor theory, you end up obeying wave equations. So the conclusion is, or should be, something like these are something to do with physics. The space of interest, as you said, is 6-dimensional. It's the projective space of the null split octonions, if you might say. Okay, except it's not really split octonions, as I keep emphasizing. It's really the one of the spaces of the triality. So that's the sense in which it could be that there's a role for 6-dimensional spacetime, and that 6-dimensional spacetime it has signature 3-3. There's no way around it. It's just the way it is. So that's about it. Now
you take some more time if you like.
Okay, I'll just take a couple of minutes. I would like to go back to a key formula that I know will probably be at least of interest to Roger. I guess I don't have time to go through all this. There's twisted geometry, and there's an idea of going from twisted geometry to fields, and I just mentioned it at the beginning of my talk. You do contour integrals. Okay, so let me see if I can go back to the. I wonder if I can. If I can't, now how do I go? I say share.
Yeah, go share and choose the whiteboard. Yeah, we see you. You can write. Yes. You can write on it.
So what I've suggested is that the equation for fields should really be a double integral of f of a twistor, and then you do a two-dimensional integral like this. So this is a function on twistor space. In order to
talk though.
Roger's saying something, George.
I couldn't.
No, okay, maybe he's on the phone, I think. Go ahead.
Oh, I thought he was trying to. Okay, to get to the field, you look at this equation z wedge x is 0, where x is a point of the Klein quadric. So that means in twistor language that it obeys this relation. That's the Klein quadric relation. So once you specify that z obeys this equation, that means z lies on a CP1. Sorry, under CP1, a C2, and you can do this integral, and that gives you a function of x. Now, I mentioned at the beginning of the talk that it seemed like it was important to go from a one-dimensional integral to a two-dimensional one. So why is that important? Well, when you do contour integrals, you have poles. So a typical thing that one integrates in twistor theory is something like ZL, the reciprocal, this kind of thing. And this actually gives you your basic massless field, which is looks like this, massless scalar field. So anyway, the point is with contour integrals, you have poles and you integrate around them. Okay, but so what's that saying is that in normal twistor theory, the key ingredients are functions that have poles, and that gets translated into really one is doing sheaf cohomology. And the key sheaf cohomology group that's relevant in twistor theory is actually the first cohomology group. But that raises the question, why is there no role for twistor functions themselves? Okay, well, the answer is that there is, because if you have a formula like this, you can just place in front of this any function of z, where this is an entire function. And so really the twistor integral formula should allow for the presence of these entire functions. And if you go back to basic twistor theory, you'll see that there really is a role for these things. It's just never been made explicit. And similarly, there's a role for not just functions of z, but also entire functions of the partial derivative, like that. So in the end, what I'm proposing, I more or less said this in Cambridge in a different language, is that you should really regard the space-time field as having the following structure. You have an input F, an output G, and then you put the field that you're thinking about in here, where these are, this is thought of as an entire function of z, and this one an entire function of d by dz. And so what you're really doing is forming a sort of scattering like this. Well, what's the bottom line? I try to make this a bit more explicit in Cambridge, if anybody wants to look at that talk. I think it's on YouTube. But the end result is that you're doing quantum mechanics where the input and output spaces are spaces of entire functions. Okay, but what's wrong with that? Well, they don't have a natural metric on them. So you end up with, you have to go beyond von Neumann. Von Neumann formulates quantum mechanics in terms of Hilbert spaces, and you think of operations like this, where the input is a state alpha, the output is a state beta, and these belong to a Hilbert space. And this is some operator. But what I'm saying is that in twistor theory, there's now clear evidence that you do not need these to be in a Hilbert space. All you need is that the amplitude to be well defined. Now, it turns out that, of course, with entire functions of z, there exists, at least for suitable entire functions, you can certainly normalize them. You can do things like, in one dimension, e to the minus mod z squared times the absolute value of f of z squared dz dz bar, that kind of thing. That will give you a norm on entire functions. And this is actually used in standard quantum mechanics. But the problem here is that there's no natural norm, because we have a symmetry group and you have to respect the symmetries. So even though there might exist ways of normalizing what you want, you actually cannot formulate it in the language of von Neumann. So I know this this forum, which has been provided by our hosts, is about going beyond sort of out there ideas. So here we have an a slightly out there idea, which I claim actually exists naturally in twistor theory, even if you cannot see it directly. And it tells you that the axioms of von Neumann are not sufficient.
Do you think this Jordan's algebraic formulation of quantum mechanics that might work better, you think? You know, Jordan, Wigner, von Neumann, this algebraic formulation using the Jordan product instead of the matrix product of Hermitian matrices. I'm just thinking aloud.
I know you guys are experts on those things. I'm not very familiar with these things.
Okay, no problem. Go ahead, please. Go ahead.
Thank you very much. That was a wonderful talk.
I could have talked for hours, but
oh yes, here.
Thank you very much. Thank you very much.
We have plenty of time for Q&A though.
Okay.
Good. So yeah, the talk is open for questions and comments. I would like to, Roger, please go ahead.
Yes, I was going to ask a question which you sort of came to at the end of your talk. You see, when I was working with, what I've referred to as bi-twistors, which is a twistor and a dual twistor together, and then you have the commutation rules, you get a triple product, multiply three things together, and that gives you a fourth. And you can, making one of them the identity element gives you the octonionic or split octonionic product. I think it's very close to what you were saying. But the question was, I was going to ask, which I think you sort of addressed at the end, was, you see, my algebra depended on using the commutation rules. You had to have the quantum commutation rules in order to get this triple product.
Yes, that's of course the key ingredient of twistor theory. I emphasized that in my Cambridge talk, but I wasn't here. I was just sticking with octonions, and I couldn't get to that aspect. Yes, there's this business of Heisenberg and SU22. You have to deal with both of them. Anyway, carry on.
Well, it was just I think it tied in with what you were saying at the end when you were talking about the operators. And the d by dz's that you had, I mean, that's basically, you have a twistor and then the dual twistors, and the twistors and the dual twistors are conjugate objects.
That's right.
And so you have the canonical commutation rules in order to get these split octonion products, or the triple product, which gives you the split octonions. You need to employ this canonical commutation rules. I wasn't quite sure how that was coming into what you were saying.
I remember that you did this thing using four things, and I know it's part of the theory, but at the moment I've forgotten how it actually works. But the basic point that is definitely that the Heisenberg commutation relations I regard as, and I did say this in Cambridge, as being the central aspect of basic twistor theory.
Yes, that's right. Also, there's something that you were saying at the end as well was reminding me of something I'm trying to do now. You see, how do I put this? I mean, one's really, excuse me, interested in doing general relativity. So you don't have it seems to me that, you see, you can express general relativity in terms of this language, where the Weyl curvature comes in and you have conformal invariant structures, which is really the basic bi-twistor stuff. But then when you want to talk about general relativity, the Weyl curvature has to come in, and you do this by using the same kind of trick we used to use before when you talk about the nonlinear graviton, and you make a curved twistor space basically out of
deforming the usual
deforming,
twistor.
that's right, exactly. So there's something very similar here where you could consider doing general relativity. That it's something I hadn't quite finished working out. Maybe haven't quite. Maybe a bit of a hopeful statement, but nevertheless, it seemed to be a lot of what you were saying seemed awfully close to what I was trying to do, and it would be very interesting to try and explore the connections between the two. I think your point of view is a bit different from mine. You were looking at different spaces, and the red space and the green space, or whatever it was, and the blue one. Whereas, well, yeah, I suppose that means you decouple them with each other or something. You have one space. Well, I wasn't quite sure how to say it. Never mind. It's not a well-defined question.
Yes, well, unfortunately, I was in Cambridge the week after you were, because I was originally planning on coming for the whole month, but my department wouldn't let me. So
I see. I was hoping to see you there, but I guess we didn't quite make contact then. Yes.
Roger, at this stage, could I ask you, what is your view on six-dimensional space-time with 3 times being an element of physical reality? And also the same question to George also, but we could start with you, Roger. Well, I mean, where does this fit in the 6D space-time?
Well, I'm not quite sure I understand how you can have 3 time dimensions. Maybe that's interpreting things in a different way from my end, because you've got to have something where the ordinary Lorentz group and so on with you one time in 3 space, and that's what's tied up with the ordinary twistor theory. So I wasn't quite sure how to interpret the 3 time dimensions that you were having in your talk. That was.
So we could come to the interpretation. I can make a comment on that, but in what way is 6D space-time with 3 times natural to twistor theory or to bi-twistor spaces? Could you say your outlook on that? That's what George is saying, no? With 6D space-times?
Well, let me say something else. You see, I don't see how space-time can be 6-dimensional. So perhaps I have a different viewpoint from George. But I do think very likely, and this is something I hadn't explored and I don't know the answer, but it seems to me very likely that your triple product things are related to strong interactions. See, strong interactions, you have this SU3, but it's really, what am I trying to say? See, it's really a proper bundle. You don't know the different direction. I mean, the 3 would be the 3 of SU3, put it like that. So it's connected with strong interactions. Do you see, George, any connection with strong interactions in what you're saying with this triple product?
Well, there is an obvious suggestion, whether it makes sense or not, I don't know, is that if you think in terms of the Freudenthal setup, you take a pair of trialities, one corresponding to 08, that's ordinary octonions, and one corresponding to 044, and you build out of them the exceptional Lie algebra E8, the non-compact version, and the compact 08 thing would represent SU4, and the non-compact 044 thing would represent the twistor theory. That's a possibility. If I don't know how seriously to take that. I've got no evidence that that would be the correct way to go. But it's very, as you say, it's very sort of suspicious that the same sort of groups show up. In the Lorentzian framework, you have U22, and in the physics framework, particle framework, you have some sort of compact unitary group. So it's very, very suggestive that one should just put them together, and that would give you If you're not careful, you're going to end up very quickly in the land of 10-dimensional supersymmetry, which is a land I would rather avoid myself.
Yes, yes. No, I think there's a lot of great interest here, and I would certainly be interested in understanding better what you're saying and see how these things fit together. But it looks very beautiful.
Thank you, Roger. So we have two questions. First, David, then Francesco. Go ahead, David.
Hey, thanks for the talk. I'll have to rewatch it because I was unfortunately in another meeting, but I was curious if you've ever thought of using D equals 4 plus 4 for 3 generations of matter, because long ago Bertram Constant discussed the intersection of SP8, R with spin 4, 4, and I was able to use CL 4, 4 to get a spinner and get 3 generations from studying spin 4, 4. So I was curious if that idea has ever come across your mind.
So you're saying that you intersect SP8 and 044. I don't have any feel for what that intersection is. This is in constant somewhere. I'll look it up at some point.
Yeah, it was in the 1980s. He says it gives 3 different copies of U2, 2. So it gives 3 copies of the conformal group with an additional U1. And I found that it also intersects to give 3 copies with SU32. And SU32 cross SU5 is maximal in E8 minus 24, which is a non-compact real form of E8. So you can basically get 3 generations with grand unified theory coming out of E8, because Lisi struggled with the 128 spinner because you need 192 for the standard model. But when you use the extra time dimensions, you can get projection operators to give you 3 conformal charts to elegantly get it to fit in 128. So, but it's hard to find the paper right now because Archive rejected it. So I just figured I'd throw out the idea.
Okay.
David,
anything that Constant did is definitely something worth pursuing. I would say that. I don't know the details.
I think George's way to 3 generations from D equals 4 plus 4 was through the exceptional Jordan algebra, because from there through triality, you could arrive at the exceptional Jordan algebra, and if you do it with the octonions, then many people have argued that the 3x3 matrices of the exceptional Jordan algebra are the correct place for fitting 3 fermion generations.
It sounds promising. Yes, I agree.
I think the split octonions are better.
Which one? The what you mentioned, the previous one?
You can make an expensive Lagrangian.
Yeah.
That's in the literature.
Okay.
I mean,
okay.
The nice thing about the split octonions, from my point of view, is the fact that there is these null things, and those things have a new geometry of their own, which is not present in ordinary octonion theory. You just
the Freudenthal phase space related to the split octonions?
Well, yes, you can build it from octonions, or you can build it from split octonions.
Okay.
The interesting thing about the E7 that I mentioned is you get the same E7, I believe, regardless of whether it's octonions or split octonions.
Yeah, I think the way you get E7 is very beautiful. It's related to a phase space. I didn't know that yet. But E6 and E8 arise more naturally, and E7 sort of stands out like a sore thumb. I have never understood really what E7 does, but here's a very good example you gave of the phase space. Yeah.
Well, that's not my work. I'm just rephrasing known work.
Yeah. Anyway, thank you. Francesco, please go ahead. David, are you done?
Sure. Thank you. I appreciate it.
Great. Francesco?
Yes, thank you. Yes, thank you. Well, it's was a really fascinating talk, and I have to digest because these beautiful diagrams and connection with the twistors. I have just make some comments on what you did in the direction that you didn't want to go. There was a long time ago, there was these duality relations pointed out by Hall and Puri about the different space-times. And something like, it is not nice that, can you hear me?
Yeah.
So,
Yes.
So for string theory, superstring theory, so of course which is okay, it's a nice mathematical object, exceptional mathematical object, so that's the interest. And you see, people used to forget that they say, okay, it is consistent for not very deep reason, just because of a Majorana by spinors exist in 9+1, so you have to compactify the extra dimension, but they used to forget that there are also the 5-5 dimension. And in fact, there is not only duality, but full triality, which relate the Majorana-Weil spacetime 9,1, 1,9, and 5,5. And this is, of course, related with the fact that octonions and split octonions they have a triality relating them, so it is not surprising. And this triality relating octonions and split octonions not only enter the game of non-associative theory, but also enter the game when you act on you have some action, left or right action of the octonions on themselves. They induce some associative structure which plays their role, enter in the exceptional group. For instance, the Fano plane, which gives the information about the non-associative structure of the 7 imaginary octonions, also give information about the 2-3 graded structure in associative algebra. So there is some very interesting mathematics that have to connect all these constructions, and I think this is a very fascinating topic, by the way.
Fully agree with you. Yes.
Okay, so you're saying
the other
actually,
point is,
you're saying actually there is some connection between 055 and 091, which is somehow related to. So to me, they're 091 is octonions and 055 is split octonions, and I don't see a connection between them. So you're saying that in fact there is such a connection.
Yeah.
yes, it is possible to formulate a connection between these come from similar construction, so to speak, and so that one can try to formulate. And then the question, of course, is which kind of physical condition, if you want to apply to some dynamical systems, have to be enforced in one case or another. So, but the mathematics, which it's quite fascinating, by the way, and I think it should be better explored. But so your talk is really fascinating, and I want to understand more, so I have to digest it. So I cannot make a comment
Thank you,
on the moment.
Francesco. Thank you. Thank you.
Thank you. Thank you.
Should we go ahead to the next question? Yeah, Michael, and then Bernd, please go ahead.
Yeah, thank you very much indeed, George. It was a fascinating talk, and it really did bring very strongly to my mind a deep sense of the extraordinary beauty of twistor theory, and the depth of unification of structure that it suggests. So thank you for that. This is probably a very badly formulated question, but at one point it was mentioned this dualization of the commutation relations, which naturally arises in several places, might have some meaning from the viewpoint of cohomology. Did I hear that correctly? I think in one of the in passing in your answer to Roger, there was a brief mention of that.
Well, I don't know exactly, but certainly in twistor theory, I won't write on the whiteboard at the moment unless I have to. But in twistor theory, when you do a contour integral to get a field, in the usual process, if the field has some negative homogeneity, you have to throw in lots of z's until it gets degree -2 to do the integral. But if the field has positive homogeneity, you have to throw in lots of d by dz's until you get the right homogeneity to do the integral. So it's natural, even in the most basic twistor theory, to have both the operators z and d by dz in the business. What I was trying to say today is that actually one should make these things very important, in that it's not just cohomology, but also the fact that a trivial fact that in any contour integral, if you multiply by something that's regular, that's has no singularities, it's a trivial fact, then you can do the same contour integral over the same space. So usually one is thinking in terms of projective twistor theory, and then the only holomorphic functions that are constant on a sphere are the constant, so it's irrelevant. But if you do it at a non-projective level, then you have all possible entire functions. So given any twistor function, you can multiply it by all possible entire functions. So you have a whole structure there. This is something that might be said to be analogous to string theory, where you have functions of a single complex variable. Here you have functions of 4 complex variables. So in other words, I'm thinking of actually the holomorphic functions of twistor space, that's the non-projective twistor space, are actually a big deal and a key part of the theory. And then also, correspondingly, the holomorphic functions of the d by dz operator. Because for every formula you have with z, there should be a corresponding formula with d by dz.
I can just interject. I remember Roger giving a beautiful presentation about 2 years ago in Oxford. You may remember my coming to record it, Roger. I remember your D's. You finished the whole of the last part of the board was full of the D's and DZ's, with kind of I can't quite remember now, but the way you had a very nice way of showing the kind of cross connections between them. You made the point that this, particularly from the point of view of the role of the split octonions, this is something particularly essential. But again, I was interested particularly in the connection with cohomology. I had one other question, which is even, I'm afraid, probably more badly posed. But the one thing I didn't quite
before you go on, I have a very silly question. Why have you got Adrian Matthias in the background there? He's somebody I used to know quite well.
Because I'm looking after his library.
Oh, okay.
Those are his books. They're currently stored in my room here. I'm looking at them because he's in exile in Germany. That's the answer to your question.
Okay.
The question I had for you was, I'm afraid the one thing probably because I wasn't concentrating enough, the one thing I didn't quite take away from your talk was the answer to the question that's posed in your title. I mean, why are these 2 additional dimensions? Why are the two out of these 6 dimensions to be thought of as dimensions of time?
Oh, well, that's very simple.
Okay, I'm sorry it's such a naive question, but
no, it's just that you have a 3-3 naturally. The thing that you're interested in thinking of as space-time really comes from the null. Let's call them split octonions, although they're not really. So you're an 8-dimensional space, and you have a null thing in 8 dimensions. And that naturally has a conformal structure of signature 3-3. And then when you break the symmetry down, you end up with space-time. So the idea is that there would be some primordial universe in which there was no time, where there were 3 times. And as things evolved from the Big Bang, somehow a time was selected. I'm
very tempted to intervene, but you finish, George. I want to say something now.
In other words, it's some kind of cooling thing. As as you cool, the symmetry is broken, and that leads you to the space-time picture. I mean,
Okay.
I'm not saying I have a theory. That's just.
But this is connected. But if I've understood correctly, this is very strongly connected to the point that when you bring in the split octonions, you have these null elements in the geometry.
Yes.
Which give you this kind of additional, and this connects with the dualization of the commutation relations.
Yes.
Yeah. Okay. Okay. I just wanted to understand. I hadn't completely misunderstood. And I'm sorry, Tajinder, you want to come in with a
sorry, Bunt, if you don't mind, I'll just make you wait a couple of minutes because it's very closely connected to what George just said, cosmology and 6D space-time with 3-3. But before that, I wanted to also remark on the point that Roger made, that what do we do with 3 times? So I have 2 things to say about that. One, that these 3 times are actually time-like coordinates on the same footing as x, y, z, the space-like coordinates. And the role of real physical time, the time that flows, is being played by something else. In my work, that is the so-called Cohn's time that arises in non-commutative geometry, or someone else may have something else playing the role of space, of time. Time is something different from time-like coordinates, what Newton would have called, I think, common time versus absolute time. So that is one suggestion from my side. The other is that classical systems live in a 4D space-time, which is our space-time, but quantum systems probe the full 6D space-time in the following sense. We are actually, some of us, 7 or 8 of us, working on the physical reality of 6D space-time. And this is what we find. Hopefully, we'll publish something in a paper in the coming few weeks. Namely, as you said, the universe to begin with was 6D. And then at the electroweak symmetry breaking, it separates into 2 copies of 4D. One is our 4D, which has 3 spaces and 1 time. And there is another flipped 4D, a second copy, a second sheet you could call it, which has 3 times and 1 space. Now this is known that given a 6D space-time, you can bifurcate into 2 copies of 4D space-time, 3-1 and 1-3, and you can do this in 3 different ways. Whether that has something to do with 3 fermion generations, I don't know. So but the part that becomes very interesting is that the second 4D space-time, its geometry is given by the weak force. Namely, if you take the SU2L's broken symmetry from electroweak, you can recast it as a Riemannian geometry of a space-time with 3 times and 1 space. And you can conversely take general relativity and write it as a SU2R gauge theory, the right-handed counterpart of the weak interaction. So before the electroweak symmetry breaking, electroweak is unified with SU2R cross U1. I can talk about this U1 later. So there is a graviweak unification before the electroweak symmetry breaking. After the symmetry breaking, it separates into 2 copies of 4D spacetimes, one which is curved by the weak force. The weak force is actually a spacetime symmetry sort of masquerading as an internal symmetry. So the gravitation, general relativity, is the right-handed counterpart of the weak force. Quantum systems experience both the spacetimes because they experience weak force as well as gravity, whereas classical systems experience only our 4D spacetime. That's a picture we hope will present in the next few months. We are quite excited about it. And I think it ties up quite closely with what you have said. And also, there's quite a bit of literature on 6D spacetimes with 3-3, going all the way back to early days of Dirac and Jordan. And I was struck by a remark of Michael Atiyah when he said that the Dirac operator was actually first discovered by Hamilton when he discovered quaternions. Because if you take the three imaginary directions of the quaternion and make a gradient operator, del by del x I hat plus del by y, del by j hat, etc., you square it, you get minus the Laplacian. Now you ask, oh, okay, I now want the Klein-Gordon operator, the 4D spacetime thing. It turns out you cannot do it, but you can do it in 6D with 3-3 signature by using what are called complex split biquaternion. So yeah, you get basically 6 imaginaries. And if you complexify 3 of those directions and you square it, you get, lo and behold, the Klein-Gordon operator on 6D spacetime 3-3. That's what makes me think that there is something very special about 3-3. And there are also papers saying that natural home for the Dirac equation is a 6D spacetime 3-3 and not the 4D space. So I think your connection between twistors, split octonion, the 6D spacetime, to me it seems it's very fundamental. And I think there is physics in it. So my picture is the weak force is involved in an important way. Sorry for speaking for so long, but I wanted to use this opportunity.
That's a nice idea. So basically, you're saying, I think somebody also in the chat said the same thing, that you start with 044 and you split it as 031 times 013.
Yes, who's saying that?
You take 013 as space time,
yes,
and
yes.
031 you keep as some other space. That's pretty ingenious.
Yeah, so I would still ask for Roger's reaction. Does he feel better about 3 times, or you rather not have it?
Not so happy.
Okay. Oh,
yeah. I think we're happy with one time dimension in
yeah, so what I was saying, Roger,
reality.
Classical systems see only one time. But how do I rule out that quantum systems experience 3 times? How do I know?
I don't know. You would need to devise some experiment that.
Also, I found, Roger, that 6D spacetime is very good for understanding quantum non-locality, because you could have time-like intervals in 6D, which when projected to 4D look like space-like. So the Alice and Bob separation looks space-like in our 4D spacetime, but it's actually time-like in the 6D spacetime that George is talking of. And that seems a way out of the non-locality puzzle, I mean.
May I suggest another possibility for thinking of extra time dimensions?
Yeah, please go ahead.
So you can use a frame field to get to some local structure rather than having some global manifold. And it's common to have a higher or lifted frame field. So then you can have enhanced local symmetry. So you can have a global spacetime that is 3+1 dimensional, yet still discuss things like spin 3, 3 or spin 4, 4 on the local structure. And when you study gauge gravity, when you look into work of Ivanov and Niederle around like 1981, 1982, for instance, it's very common to put the fermions as a scalar of the global manifold, then gauge the Lorentz group and have the spin of the fermions come out from the representations of the local gauge group. So when you do that, then you can raise the symmetry and discuss these extended symmetries with extra time dimensions. And it's a somewhat natural way to do it. I'll also mention, however, that the string theorists would essentially say that if you have a space-time with extra time dimensions, that it would lead to problems with ghosts. And
I agree, but that's why I think it's important to decouple flowing physical time from time-like coordinates. I will get somebody else to do the physical time, So it's like the 6D space-time manifold evolves in an external physical time.
Exactly. I did work on that as well. So Itzhak Bars discusses how to have D = 4+2 space-time And what he does he doesn't run into issues with unitarity or ghosts, because he essentially adds in his integral over 6 dimensions, he adds some delta functions to collapse it back down to 4 dimensions. And so I was able to do that with d equals 3 plus 3 as well, but it's not in the literature because none of the referees of the journals like want to read it. And so you can formulate a 6D or an 8D global manifold that has some d equals 3 plus 1 inside. But quite frankly, I mean, if you have those delta functions, it doesn't really give you anything extra that you need because you're just integrating them out anyways.
No, so I would do more than that, because if I integrate out once to get 4D, there's a different way to integrate out something else to get a flipped copy of 4D, and I want to relate that to the weak force. Somehow bring gravity and the weak interaction at par.
Yeah, I mean that spin 1, 3 that's commuting with the spin 3, 1. I mean, there is an SU2 in there that you can play with, but yeah, I mean, look at Bertram Costant's work, which I shared in the chat. He provides some good motivation for 3 conformal structures, and you know, the association of twistors with massless fermions is very well established.
This has been a fascinating exchange, but I think I have to abuse the privilege of the chair by saying we have been keeping Brent waiting a very long time to ask his question.
Yeah, I'm so sorry. I'm so sorry. I'm so sorry. Please go ahead.
So first, thank you very much, Michael. Thank you for the nice talk, Mr. Yeah, and it's not a problem. So I will just add something on what has been said earlier. As usual, I'm here for the historical comments. So the idea to attach extra time-like dimensions to formulate it as carefully as possible is actually quite old, and is also related to the Dirac equation. So it is an old paper from 1935 by Schouten and Van Danzig, so 2 Dutch researchers who proposed this to add at that time 1 extra time-like dimension, so a kind of a Kaluza-Klein theory, but with an extra time-like dimension instead of an additional dimension of space. And because we talked about Jordan algebras, I cannot resist the temptation to mention that Jordan also worked on something like this in the early 1950s with extra time-like dimensions. So he actually also wanted to formulate a unified theory not only of gravity and electromagnetism, but also of the weak force. And for this, he used a space-time with 3 real dimension and 3 time-like, so imaginary directions. So basically the 3 plus 3 space-time we are talking about at the moment, and he had also the same motivation behind it to unify the weak force with gravity. At that time, they were still developing a theory of the weak force. So his main motivation was to find a way to how to formulate a theory of the weak interaction. And to give, he called it the neutrino charge. I think today we would call it the weak charge. So this was something he did in the early 1950s, in 1952, actually, after being asked by Heisenberg because Heisenberg was also developing his unified field theory at that moment, and he asked Jordan for help, and then Jordan worked on a 6-dimensional space-time to unify gravity and the weak force. And something which might be of interest, or maybe
can
not.
Can you repeat that? This is there in Jordan's work already?
Yes, that's what he said.
Sorry?
The unification of gravity and weak force in 6D is already there in Jordan's work?
In the paper from 1952, so he had 2 motivations. First of all, he wanted to find any kind of theory how to formulate a weak interaction. And then he wanted to unify it with gravity and electromagnetism. So he wanted to formulate like Kaluza-Klein theory was aimed at unifying electromagnetism with gravity. Jordan wanted to go 1 step forward or 1 step ahead and also unify the nuclear force or the weak force. He didn't, for some reason, he never looked into the strong force. I don't know why.
Yeah, I think
but he was
cannot
looking.
do that. You have to go to even higher dimension. You'll have to go to 10D. If you are
okay, maybe
6D,
that was the reason.
if you're in 6D, you can do weak and gravity.
Okay, maybe that was the reason. He was he was radical at that time, but also conservative. So he also had some stop mechanism in himself, which stopped him from going to even more radical ideas. But in 1952, he wanted to use the six-dimensional spacetime to unify the nuclear interactions. I have to be careful because weak and strong was something which at that time was not quite in use, at least not in the way we understand it today. So I have to be careful. And he used a six-dimensional spacetime. He was in turn inspired by Julius Podolansky. This was a Polish, German, Jewish, Dutch scientist who at that time was in England and in Oxford actually. And he also wrote in 1950 a paper on extra time-like dimensions. And Jordan then took this as an inspiration to formulate his theory, but he only did it very briefly, only in 2 papers, and then he abandoned this line of research. He always had an interest in including also the nuclear forces into his ideas on unification on Kaluza-Klein theory. That's why I also looked at more general geometries than Riemannian geometry. But in the early 1950s, he was also looking into extra time-like dimensions. What might be of interest, also for the people who, for very right reasons, question the use of extra time-like dimension, was the way Jordan did it. He did not use an ordinary Riemannian geometry. The extra time dimensions have a different nature than the ordinary time-like dimension we use as coordinate time in 3+1 spacetimes. In these extra time dimensions, the symmetry group was different. So you cannot, in a sense, you cannot rotate freely in this extra time dimensions. He used a special geometry which makes it impossible, the same like Podolansky. So they restricted the kind of rotations and movements you can do in the extra time-like dimensions. At that time, they didn't do this to, well, Podolansky did it to get rid of ghosts, but Jordan did it to get the right kind of theory in 4-dimensional spacetime. So he applied these restrictions not to get rid of problems, but to get the right kind of unification of gravity and the electromagnetic force and the nuclear force. So it might be that his attempts get you an additional advantage that they get rid of some of the conceptual problems. Because if you would use the extra time-like dimensions like you use our ordinary time-like dimensions, you wouldn't also not get the right kind of theory unifying electromagnetism and the nuclear forces. You would get something very different with too many fields, even for particle physics standards. So this was the reason why he had to restrict the geometry of the extra dimensions and to get the right kind of symmetry group. So his idea was to get a space-time which has a symmetry group, which is the unification of the 4-dimensional group of coordinate transformations with the gauge groups of the standard of the nuclear and electromagnetic forces. That's why I used a different geometry from Riemannian geometry, and the extra time-like dimensions have a different kind of ontological status compared to the time dimensions we use in physics to describe dynamics. Okay, so now I also had the chance to give a very long explanation and talk, so I'm done now, and maybe this was helpful.
It would be very nice to have some of those references if you want to send them to us.
Yeah, I can send them, of course.
Jordan, 1952, you could share with us. Yeah, I can pass it to the group. Yeah, thanks.
Okay, then I will send you the papers, and then you can share them in the group.
Just a small addition to what you said, Bert. I think no doubt Jordan was a visionary. So much of these things already. So one thing which probably came later is that you cannot directly unify weak with gravity. You have to first have electroweak, so which is SU2L cross U1Y. Then you have to write gravity as a SU2R gauge theory, which is part of SU2R cross a U1Y prime, which is different from the weak hypercharge. I have an interpretation. So you have SU2L cross U1, you have SU2R cross U1Y prime, which is SU2R is general relativity. And then you unify these into something like a SU3 cross SU3 structure. So, yeah, that's all. I mean, maybe right now the time is ripe for unifying gravity and weak.
It sounds promising.
Yeah, thank you.
Presumably Jordan didn't know anything about the strong interactions, really.
No, not in the early 1950s.
Yeah,
Probably not.
as you know, Bern, they also a well-known theorem in the Kaluza-Klein scenarios that if you want to unify weak interaction with gravity, you have to add 2 more dimensions and go to 4 plus 2, 6. If you now want to unify with the strong force also, you need 4 more. 4 plus 2 plus 4, 10. That's why 9 plus 1 is very interesting, but I think they got some things wrong. I mean, they should be working with octonions and not with 9 plus 1s. As you know, SL2O is the double cover of SO91. So don't work with SO9, work with SL2O, which is a much better space to work with.
It's somehow a pity that Jordan overlooked the connection to the strong nuclear force, because he was the one introducing the octonions into physics. So he was quite close, but he missed the final piece of the puzzle, I guess.
If Jordan were to come back today, I think he will clean it up very quickly.
Probably, yes. Just to add, so what Jordan did, he had a 6-dimensional space-time. The 6-dimensional space-time should unify gravity, electromagnetism, and the weak force. So all 3 together. Then he had a 5-dimensional sub-space-time, so to speak, which only unifies gravity and electromagnetism. And then even then he had the ordinary 4-dimensional space-time where only gravity is residing.
That's very interesting. So for us, it is not gravity and electromagnetism, it is gravity and Mond. Electromagnetism is unified with weak, but gravity is unified with, so we try to get Mond, Milgram's Mond. He'll talk about his work in December. We get Milgram's Mond out of this U1 Y prime.
May I ask a question to Professor Penrose, if he doesn't mind? In case you use a different geometry from, let's say, Minkowski geometry or Riemannian geometry to add additional dimensions of space and time, so if they have a different geometrical nature, let's say, would this somehow elevate some of the problems related to extra dimensions, or are extra dimensions of space and time in general problematic, regardless of the kind of symmetry group you...
The functional freedom is, each time you add an extra dimension, you enormously increase the functional freedom.
Okay.
And you make a theory that looks like what we see, I don't really see. So I'm not very happy with these extra dimensions.
Roger, your concerns.
Thank you very much.
Also, when the extra dimensions are time-like?
Well, that changes the picture altogether, really. I would prefer to think of the 3 plus 3 as, think of this as the complex projective 3 space in twistor theory. Then you have the light rays, you see, which the space of light rays is 5 dimensions, and the space of projective twistors is 6 dimensions. So you've got a 6 there already. And you might interpret that in some ways, 3 plus 3. That's the best I can do, I'm afraid. I find it a lot of difficulty trying to make this relate to ordinary space-time, ordinary physics. Because ordinary physics, you've got functional freedom, which depends on the 3 space dimensions. Yeah. You increase the time dimensions, I don't know what it does, but I think the functional freedom will go up enormously.
Well, actually, yeah, Roger's right. If you look at if you look at projective 3 space and you go away from the null twistors, then you take the log of the Kähler scalar, log of what I call z dot z bar as a Kähler scalar, then indeed you get a 3-3 metric on the non-null twistors. Yes. It's right there. It's sitting right there. Yeah, that's of course, that doesn't necessarily say it's anything to do with space-time directly.
Well, not directly. That's right. It's not space-time. It's a different space.
So I think if we make the claim that classical systems live in 3 plus 1 4D, but quantum systems experience 3 times and live in 3-3. So I want to know, how can this statement be disproved experimentally or theoretically?
I'm not quite sure what the statement is.
It's like saying a quantum particle experiences gravity as well as the weak force, whereas the classical particle, which is macroscopic, experiences only gravity. And the experience of weak force as well as gravity can together be cast as if these two were a unified geometry in 6D, provided we can do it.
One way that you could interpret that is to have Feynman diagrams, and you could have loop integrals such that all the virtual particles could integrate over 6D momentum variables. And so in principle, you could start calculating scattering amplitudes such that the loop integrals are in higher dimensions and see if you get different results. I don't know.
Okay, thank you. Thank you. Roger, you were about to say something, I think.
Well, I've forgotten now, so sorry.
Okay.
Yeah.
Can I just come in as say, I mean, in fact, the question I was about to ask is the one which Roger has just answered. You know, namely, what is the really most general basic objection to this increase in space-time dimensions that you know, that he feels is somehow intuitively sort of unphysical? And it just is you completely lose any kind of constraint over the function space of the theory.
I think the trouble is it's my objection to string theory. When you add all these extra dimensions, then people don't realize that you just flood the whole physics with all these extra functions.
Well, string theory is the perfect exemplar of this. You have absolutely no control over
with that, I agree, Roger. I mean, I think one can safely say today, string theory is not the correct theory of unification of forces. I would leave it at that and forget it.
I think most of us.
I think this is possibly the only forum where that would go down without comment.
No, for example, I mean, I'm a small fish, but I can say this face to face to Edwin and ask him why does he disagree with me. They don't explain anything. People say they don't predict anything. I say prediction will come later. First, can you explain what we see? Can you explain why the muon is 200 times heavier than the electron? No, they cannot. Then how can they have a theory of unification if they cannot explain what we see?
Well, I think in defense of string theory, which I myself am not a fan of, it's a tremendous mathematical edifice.
I agree. I agree.
Presumably there is some structure there. And if you look hard enough, you might find some physics. But as you say, as far as at present, I would say there is no physics there.
Yeah, so to my understanding, what they missed out is the octonions. I think that they are very important. They've been working with the background space-time in perturbation theory, and the background is Minkowski, and it is labeled by real numbers. My point is, in quantum theory, if you use real numbers to label a background space-time, that is an approximation. You will never get to the true unified theory. Even at low energies in quantum field theory, background spacetime should not be described by real numbers. If you want a deeper theory, you have to go to these non-commuting division algebras like quaternions and octonions, and they seem to have a great dislike for octonions. They want to work with E8, but they don't want to work with octonions as physical quantities. I don't understand.
The problem is they couldn't figure out how to work with it mathematically in the 1970s. So it seems like John Schwartz was very fascinated with the octonions at Caltech. And so, I mean, there are some researchers like Michael Duff and Mia Hughes are, experts in supergravity who have explored the octonionic representation. So when Mia Hughes gave a talk, John Schwartz got really excited. But basically what happened is they couldn't publish any papers in octonions, and in the 70s, they couldn't figure it out. And so then no one in the field caught on, and time went on.
Okay, thanks. Thanks for the clarification. I appreciate that. Yes.
Can I come in with a very quick comment on that, Tajinder, if that's okay? The comment leads to a quick question. there's a rather fascinating parallel there between what David's just said, that in the 1970s, one of the reasons that octonions didn't get taken up was because it was difficult for people to see how they would figure in physics. Of course, exactly the same thing happened almost 100 years earlier with the quaternions. You could even go back to, say, the 1870s, more or less the same thing happened with the quaternions. They had flourished as a very exciting program in the development of algebra, but they did not, in the end, turn out to really turn the key into new physics, at least not at that time. Which brings me back to one quick question. The O55 is the group of the split octonions, yeah?
No, it's the group of the 2x2 matrices over split octonions.
Sorry, okay, my apologies. Okay, so it is O55. That's the group of the matrices over the split octonions.
Yeah. If you have the SL2OS.
Right. Okay. I'm just thinking
linear group over 2x2 matrices.
Okay.
Octonions that are essentially Hermitian or anti-Hermitian, however you define it.
Yeah, I get that. The question is kind of inspired, connects with my remark, remark about this kind of loose parallel between the quaternions in the 1870s and the octonions in the 1970s. Does anybody know, I guess this is the kind of question which Basil Hiley and the people very interested in the Clifford algebra approach would possibly know the answer to, how the O55 groups actually fits into the Bott periodicity in the Tower of Clifford algebras. I know that the octonions do fit into the to the Bott periodicity, but I'm not quite sure.
Yeah, you can have Bott periodic structures with split groups as well.
Yes.
So I mean, split octonions themselves, nested multiplication of split octonions without matrices can give you spin 4,4 transformations. And there you have like an 8-dimensional object, just like with the octonions. And so you can, in principle, have Bott periodic extensions with compact or non-compact structures.
That's what I understood. That's very clarifying. Thanks for that confirmation. There's a bit of a debate going on in that community, in the kind of Clifford algebra, centered group at the moment, as to whether split octonions or Sedanians are the kind of correct thing to be looking at in terms of the the properties that they think that Bott periodicity is telling them that they ought to have in the division algebra in question, that they need for the kind of unification program that they have. Anyway, thank you very much for the answer. I would, because I occasionally talk to them, as it were, on the other channel, and it's always very interesting to get their feedback to things which are raised in OSMU.
Yeah, Michael, just before passing on to Bernd again, just a small comment. When you say quaternions were forgotten, of course, I agree with you, but we could qualify that to say they were forgotten in favor of the equivalent language of vectors and vector analysis.
Well, except I would have to come in there. I don't think it was exactly equivalent. That's the problem. It was not conceptually equivalent. I mean, they were, of course, they were regularly rediscovered. I mean, Dirac, of course.
Yeah, I agree with you, I think. And I think it was a tragedy that we forgot quaternions, because when the Dirac equation was discovered and gamma matrices were added by hand, had you been working with quaternions, you wouldn't need gamma matrices. You just have to write gradient operators using quaternions, and the square will give you Klein-Gordon. Gamma matrices are a backdoor entry for quaternions into vector analysis, so to say.
Yes, to Jinder, as my old friend Bill Orville would have said, you are singing to the choir.
Yeah. So, or maybe we should be saying that to the string theorists.
The biquaternions are very natural for Maxwell's equations, and they're isomorphic to CL3. And CL3 or C cross H allows for representations of the Lorentz group. And Maxwell, in his his second or third version of his treatise, probably didn't quite realize that. So in the late 1800s, people didn't fully grasp the notion of how the quaternions are really more for rotations rather than vectors. And obviously you can find the quaternions as the even part of that Clifford algebra from there.
Well, I could say people generally, but of course Clifford did. That was one of the remarkable things about Clifford's, being so far ahead of his time. But yeah, in general, that wasn't grasped. I agree.
I'm fascinated that you can write Maxwell's equations as a single P cross H equation. I just think that's beautiful.
Yeah.
I think probably all of physics. I think we'll hear from Andrew Hamilton in the next OSMU talk, geometric algebra and unification. So I think the picture there is that you take any physical theory, you should be able to recast it using Clifford algebras and division algebras. So maybe time for Bernd now, Michael. We keep stopping.
Yes, of course. Yes, I'm sorry, I didn't mean to take up your time. Yes, by all means.
Time I will be
probably
brief.
be drawing to a close.
I promise. So in defense of string theory, and because Francesco is here, there have been attempts also to introduce the octonions. You mentioned this earlier. And there are also some papers now where they don't use the classical space-time for the extra dimensions, but non-commutative and non-associative algebras to describe the extra dimensions. So they, at least there's a few papers or a few groups which have abandoned the idea to attach the classical space-time to our ordinary space-time and use non-commutative and non-associative structures to model the extra space-time. So this is in defense of string theory.
Or it happened during the string revolution?
No, these papers are in the last 10 years. There's an older paper by Witten, actually, from the 1980s, where I said we will need a commutative but non-associative algebra to describe string theory. This was from the 1980s, but they didn't catch on this, and it was until
let me ask you, Bernd. I agree with these developments. Of course, one could add that the supersymmetry is now a hazard. People are now writing papers on non-supersymmetric string theories because string supersymmetry has not been discovered. But I would like to ask you, Bernd, your picture. What did string theory miss because of which it is not able to explain the world? Everything is there. You're saying octonions are there.
It's a difficult question. I think you could point the same thing at any attempt to unify at non-commutative geometry, at loop quantum gravity. At the moment, none of these research programs is very...
No, I would say that those of us here who are now looking at algebraic unification, following Gursi and Gunaydin, and for Tony Smith and Dixon, and the more recent people working with octonions and particle physics seem to make more promising progress than has been made in string theory, in my opinion. It's not.
This might be true. So if I, my guess is that they have, this is only a hint and a guess, and I might be wrong, and I don't want to blame string theories for anything, just to make this clear, but my guess is that a certain important mathematical and also conceptual insight is missing in all attempts if you try to use the octonions. I think what most people are missing is that if you try to use the octonions, probably you have to go beyond the formalism of quantum theory. So we're going back to the end of his talk. You have to live outside of Hilbert space. So what we're actually doing here is going beyond quantum theory. We're not only unifying forces, but if you use the octonions, it's the same step you had from classical mechanics to quantum mechanics. So people always try to quantize gravity and quantize unified field theories. If you use the octonions, you go beyond quantum theory. You super quantize, if you like this word. And I think this is always the stumbling block. So if you look at the 1930s, when Jordan tried to introduce the octonions, he hoped that the octonions will provide many examples of exceptional Jordan algebras. So a really non-associative version of quantum theory, where you can take basically all of the traditional axioms from Hilbert space, and all you change is just you add non-associativity. This was his original hope. He wanted to go beyond Hilbert space, but not too far away from Hilbert space.
I agree.
And then he noted...
What we are seeing now is that better not to think of gravity as a spin to field which curves space-time, but think of pre-gravitation as a SU2R gauge theory, which is the right-handed counterpart of the weak force, that's much more rewarding because SU2R cross U1Y prime is also perturbatively renormalizable for the same reasons that electroweak is renormalizable, but the 4-point Fermi theory of the weak interaction is not renormalized. Same reason gravity is not renormalizable, but when you think of it as a SU2 cross U1 gauge theory, things start working better. And I think this is also missed by string theorists. They always thought of gravity in the conventional Einsteinian sense, but I think that sense is emergent and not fundamental.
This is once again a very general problem for most. I mean, also the loop quantum gravity community tries to quantize Einstein's theory. So they start directly.
In my view, you cannot quantize gravity without unifying it with the other interactions. That's my picture. So I would say loop quantum gravity, while very insightful, will always face this limitation. You have to unify.
Here you're on the same side as the string theorists who also said you cannot unify quantize gravity without unifying with the other forces. That's a good heuristic argument. If you look at the Einstein equations, the matter tensor contains all of the fields in the standard model. If you quantize,
you have fermions. Fermions have other interactions which are stronger than gravity.
Yeah. So they're very good arguments to say that you have to unify.
Yeah, but, the string theorists are going back on their own word. They now talk of string theory as a complete UV complete theory of quantum gravity without saying anything about unification. Because the viewpoint is we are not ready for unification. We need beyond standard model experimental evidence. So Peter Voigt writes that in the string theory community, anybody who's trying to unify these days is looked at suspiciously.
I have to add something.
That's true across the board. It's just hard to get papers published on grand unified theories at this point because everyone's kind of sick of it. I don't think that's really string theory. It just so happens that the string theorists have been pioneers on finding grand unified theories. For instance, even exploring aspects of flipped SU5 gut, which hasn't been experimentally ruled out yet. If you look in the literature, I mean, all the works in string theory.
No, I agree. But if they take the viewpoint that because they could not do it, it cannot be done. That's the objection. You couldn't do it. Well, let's look at what were the reasons why you couldn't do it. Let's address those reasons. And maybe things like algebraic unification will go beyond that.
I mean, but they have done a lot of unification models. The main issue seems to be the minimally supersymmetric standard model, but there are at least two ways to bypass that.
My point is they don't explain anything. They don't explain what we see about the standard model. I want a derivation of fundamental constants. I want an explanation for 3 fermion generations. And this explanation should be unique. It should not be that you do this and you get 3 fermion generations. You do that in string theory, you get 4 fermion. There's a free for all. It's not a theory. It's a framework.
Yeah, it's definitely a framework. I mean, it should just be called like membrane theory, as it's like quantum field theory generalized to membranes, essentially.
Absolutely. I totally agree with that. And we want more than that.
I conjectured at the end of my talk in Cambridge, based on a discussion with some features of what Jörg Freundin had been saying, that string theory was actually dual to Penrose's theory of spin networks. That's based on the fact that one of the primitive amplitudes that you get in spin network theory, if you do it appropriately, is actually the beta function, and the beta function is the key ingredient in the basic string theory. So it's a very weak link, but it's certainly not ruled out. If that's the case, then it's clear that string theory is incomplete in the same sense that the Penrose spin network theory is incomplete.
Yeah. Thank you, thank you. So the viewpoint which I support for string theory, fundamental entities are extended objects, and different modes or different vibrations of this different object, or this fundamental object, are different elementary particles, including fermions and bosons. I think this idea is beautiful. I think it's also correct. But what after this? Why are they unable to recover the observed SU3 cross SU2 cross U1 and general relativity given this fundamental object? I think something is wrong, especially compactification. I think compactification is not a good idea.
I may add something to
I
this.
completely agree.
Sorry. Go ahead, Mr. Sparling. Sorry.
I'm just saying that the whole idea of compactification is not good, in my opinion.
I agree, yes.
I think
that's one of the problems, yes.
I think that the problem with compactification comes about because you try to still use the Riemannian framework,
yes,
and then add extra dimensions which you then have to hide. So I think if we have to add extra dimensions, they will be different from the dimensions we have on a macroscopic scale. Anyway, the string theories say that the extra dimensions are compactified at the Planck scale, where we expect geometry to change due to quantum effects. I think one of the most conceptual problems, and I'm willing to be corrected about this, about string theory, the basic idea is interesting and good. Start with extended objects instead of point-like objects, but then they start with a kind of classical theory of extended objects and then quantize this theory.
yes.
It should come from a more deeper either quantum theory or generalization of quantum theory, where this is inbuilt right from the start, where you don't have to take a classical theory and quantize it. And if you start with, there was a reason why people use point-like interactions at the beginning of quantum theory. So the first point is, how do you formulate quantum theory which does not rely on point-like interactions? This is something which
and does not rely on space-time labeled by
or on space-time labels.
Points. Yeah. So I think one way to make progress is to replace that point structure of space-time by a non-commutative, non-associative algebra and try to redo quantum field theory of extended objects in such a background. And I think that will be useful.
This was basically, in the end, Jordan's ideas. He said, we know that field operators are functions of space-time coordinates, and he said, we need something which replaces space-time coordinates, so we need an algebra which goes beyond a commutative associative algebra of functions on a space-time, and this algebra needs then to be merged with an algebra of field operators, or we need to develop algebras of field operators with something replacing space-time. And this was Jordan's idea, to go to, in the end, back to non-commutative and non-associative kind of algebra which replaces space-time, and field operators would then be operators acting on this algebra, or would be functions of the elements of a very abstract algebra which replaces space-time. This was his idea.
I find Stephen Adler's trace dynamics very useful here. You take matrices to describe fundamental dynamical variables instead of real numbers. These matrices have components over, let's say, the 8 directions of the octonion. The matrix has 8 components. Matrix 1 times 1 direction plus matrix 2 times. It's like position vector over 3D space. Replace that by a matrix valued vector over the space, octonionic space, something like that. And that's one way to go. Yeah.
Of course, with trace dynamics and matrices, we are back to the very early days of quantum theory. This was introduced already next year, 100 years ago, in the very first paper by Jordan and Born on quantum mechanics.
Yeah, I agree.
Sorry, George, we're a little late.
We are a little late, but we need to rediscover.
We need to rediscover. This is a quite interesting situation at the moment in the foundation of physics, that you have to go back to the beginning.
The problem is, I think, Ashutosh is there. Unless we make a prediction different from QFT applied to the standard model, maybe nobody's going to take us seriously, irrespective of how beautiful our theory is. We need to make a measurable prediction distinct from QFT. Right. So, and what people say that we are able to explain something using algebraic unification, but explanations are not enough.
Well, I mean, I don't know if it has to disagree with QFT. I mean, you already have Nima Arkani Hamed coming up with completely different structures such as amplitude-hedra, which are not foundational in the typical principles of quantum field theory, yet he's finding scattering amplitude results of quantum field theories or supersymmetric ones. So I think we should also pay attention to this idea of essentially ideas from category theory. I look at it as a reformulation of quantum field theory that's happening right now. I mean, you could say that's a different theory itself. It starts to turn into a semantical argument. So, but I think in time we'll be in a position where basically more rigorous mathematics can be applied to some framework that essentially more or less is a reformulation of quantum field theory. That's just how I prefer to word it. But yeah, it would give us deeper insights into the true structures, because we still don't really understand non-perturbative Yang-Mills theory, for instance. Like, there's still aspects of quantum field theory that we don't even understand. So maybe we just need to, maybe another way to look at it is just quantum field theory isn't complete yet.
Yeah, but what is your picture on this idea that we need to remove real number-based point structure of space-time from quantum field theory to make progress?
Yeah, I mean, that's totally fine. You can you can just focus on the solutions of problems rather than formulating in space-time. I mean, if you're going the amplitude-hedron route, that's kind of the point. It's like, at the end of the day, all this data relates to scattering amplitudes. I mean, I think they're exaggerating on how ubiquitous scattering amplitudes are, but still, you can formulate these things without referring to space-time, and you just get these abstract structures in some auxiliary space. But you could also, but even us, when we're looking at these, expended space-time symmetries, we're still kind of grounded in space-time. So, if we're using split octonions and then referring to conformal groups and getting back to space-time, it's still pretty close to space-time.
Yeah, I also want to add one little side remark that, in my view, if you want to have a successful theory of unification, it must satisfactorily explain collapse of the wave function, and it must account for quantum non-locality. In my view, those are test beds, and these are test beds that I personally feel string theorists think are not important test beds, and that's another very sore point of disagreement, that something needs to be done to quantum theory before you unify, so that you are able to explain these things without appealing, say, to many worlds. It appalls me how they think many worlds is an explanation for the measurement problem.
Well, the amplitude-hedron picture, it leads to emergent locality, emergent unitarity. So it's hinting that there's this deeper structure that is non-unitary and non-local.
Yeah, I heard Nima saying that, but he puts it as if he's the first one to say it. But this has been around for quite. Roger knows this better. He's been saying this for a few decades, that quantum mechanics is an approximate structure. And if you hear Nima's talks over the last few years, they are beginning to be like, maybe quantum mechanics is approximate, but with no reference or citation to the so many people who have thought of this already. This, you see, it's a string theorist doing a turnaround, which is amazing.
Can I come in very quickly on that, Tajinder, because I very, very strongly agree with what you just said. I think the problem with the Nina Arkani Hamed stuff, it is, of course, absolutely fascinating. It's very clever. But as you say, it seems to me really just a reformulation rather than explanation. It turns out that you can reformulate all the phenomenology of Feynman diagrams, etc., in this much more abstract setting. And you have a beautiful set of mathematical recipes which suggest all sorts of further underlying linkages. But there doesn't seem to be any fundamental guiding idea there conceptually as that will give you any handle on what the starting point for thinking about the foundations are. Whereas, sorry, if I can just say very quickly, whereas I think the route that Roger has been pursuing, I'm the last person to try and put words in Roger's mouth, but it is that we do actually need to deepen our understanding of we do actually need to deepen our understanding of the geometric structure, the existing default conception that we have of space-time, and indeed probably in a direction which involves giving up the notion of points as the fundamental ingredients of any space-time geometry, and the test of any such program will be whether it provides a possible explanation for things like quantum non-locality. And that's why, just to sign off on this kind of take-home message, that's why I keep sort of raising the issue of cohomology, because it seems to me that the deepest idea that mathematics has recently given us about space is that our most general framework for thinking about space is as thinking about what acts as a good carrier of or good support for cohomology theories. That was the great achievement of Grothendieck. It seems to me it was the conceptual take-home message of his achievement, and that has yet to be worked out in the kind of detail that is required. But that the role of cohomology and indeed category theory, which has also just been mentioned by David in this connection, in deepening our understanding of space-time geometry, is going to be the route along which advance lies, and that all of these ideas coming from amplitohedra and things, and the very rich mathematical phenomenology they bring with them, will fall into place within some such picture, rather than being itself the kind of guide.
Right.
At the moment, they're just a set of admittedly very effective recipes, but I think that the really deep idea is going to come from deepening the understanding of space as whatever acts as the carrier of cohomology.
The 2 points. Thanks, Michael. Thanks very much. 2 points.
Sorry, I'm sorry to burble.
Yeah, firstly, I remember when I first read Roger's Emperor's New Mind when it had just come out, early 90s, I think, Roger. Yeah, you have a statement there about quantum non-locality, saying that it's such a big puzzle that it's an indicator that our understanding of special relativity is in for an overhaul. I remember those words. And today I think that the answer, the overhaul that I would vouch for, is a 6-dimensional space-time with 3 times. It is a very nice way of understanding how original locality in 6D when projected to 4D starts looking like non-locality. That's one possible answer. And but you still hold that, Roger, that special relativity is in for an overhaul if we have to understand quantum non-locality?
I can't remember what I said in the Emperor's New Mind, but on the other hand, I certainly think we have to have quantum mechanics improved. The collapse of the wave function being something which is missing in standard quantum mechanics. And that, my own view, is that is involved with combining it with general relativity. Now, I don't quite see why increasing the number of dimensions of time helps us with that. I think we do need, well, cohomology, as people were just saying a moment ago, is very important in understanding how twistor theory works, certainly in curved space-times. So if you want to talk about general relativity, I think it's very likely we have to think in terms of cohomology ideas. And using well, cohomology comes naturally in twistor theory, especially when you have curved space-times. Well, not when you have fields, if you like, then the integrals really are expressing cohomology. And I think the same idea must apply to the bi-twistors, at least when you go to these split octonian things and all that, things that George was talking about. I think that cohomology has to play a big role. I think, as somebody was saying already earlier today, but I think it has a big role to play in trying to go beyond flat space-time descriptions.
Thanks, Roger. So collapse the wave function, I agree. What about quantum non-locality, quantum systems being able to influence outside the light cone?
Well, that's true too. You see, I mean, this is a different talk, but you see what you find, and this isn't even necessarily twistor theory or anything. If you look at relativistic collapse of the wave function theories, you are led to this curious idea that you need a difference between what I call quantum reality and classical reality.
Yeah.
And quantum reality you cannot ascertain, but classical reality you can. You can confirm quantum reality, but you can't ascertain it. And then you can explain the non-locality that you have with, say, Alice and Bob situations. You have quantum entanglement, and the idea of quantum entanglement in a relativistic context leads us to this picture of quantum and classical reality. And I think you really got to look at that carefully. And a theory which would involve that in some serious way.
Thank you. Thank you.
Yeah.
Thank you. David, the second comment was just asking you for a clarification. Like Michael's mentioned that Nema's framework is really a different framework, not really going beyond insofar as fundamental concepts are concerned. But you are saying, Nema's already hinting at non-unitarity and non-locality in the underlying theory. Where does he come to this from?
So he develops these amplitudes as volumes coming from this kinematic space. And this kinematic space has nothing to do with space-time. It's very abstract. It has mathematics that's associated with inspirations from Grothendieck, one might say. And it leads to structures that are inherently non-local. And we've been talking about how quantum mechanics has non-locality. I mean, it's what I meant in the chat is it's a very trivial statement. I mean, obviously, non-locality relates to is non-local in nature. And also, I mean, measurement collapse, you're saying we want something that describes measurements, collapse of the wave function, which is a non-unitary process, right? Because it's the evolution of the Schrodinger equation in between measurements that's unitary. I'll also throw in, I believe there's a researcher named Brody who discussed non-unitary quantum mechanics and also discussed quaternions. So that's just a little nugget. But and going back to that kinematic space, it's suggesting that there's this more abstract picture that it suggests a new foundation to, forget space-time, ground yourself in this kinematic space, and there maybe it turns out it will be helpful for understanding a more fundamental origin of non-locality in quantum mechanics. And I'm just thinking of this now because I'm thinking about what Roger Penrose was saying and just thinking about the non-unitary aspects. I don't know if anyone in that community has explored the measurement problem in quantum mechanics, but it is true that measurements are non-unitary. So maybe that's a hint that it's worth exploring more. If anything, I think it's maybe we're all climbing towards the same top of the same mountain, but at different points.
Yeah, but
we haven't seen all the vantage points yet.
One interesting facet of that is that string theorists through NEMA are now beginning to climb the same mountain, which many of us here have been climbing for a long time. They're coming around without admitting or without attribution. Well, anyway, that's a social thing.
Nothing new.
Nothing new.
No, I won't be surprised if one day string theorists say that they are the ones who espouse the problems of quantum theory and found their solutions as well.
May I ask something? Oh, sorry, Mr. Penrose wanted to talk.
I'm done. I think, Michael, you decide now when we should.
No. Well, this has been such a fascinating discussion.
Yeah.
I would like
I
think we probably should be drawing to a close fairly soon, but perhaps Brent has...
George, I hope you are not overly tired. You gave the talk and now you're having to sit through this.
Yes.
Just a brief comment on my question in the chat.
Sure.
To David, to be fair, do you mean with non-local non-locality is non-local, you mean that we will also then have non-local interactions, not only non-local correlations, but true non-local interactions. Is this what you mean with non-local means non-locality?
Well, I suppose right now they're focused on exploring theories that are conventionally thought of as being local, but the main point is simply that the structures in these kinematic space, when you look at those structures alone, they seem to be inherently non-local. Now, I don't know how much they've explored, non-local theories with that framework. To be frank, like the amplitude-hedron was used for planar n=4 super Yang-Mills theory, which isn't even a theory. It's not a theory. They just took the simplest Feynman diagrams out of the simplest theory and threw away all the complicated diagrams and then claimed that they could get stuff to infinite loop order, but it's not even a theory. So there's still a lot of work that needs to be done in just even exploring, theories that we understand, let alone going to some, deeper theory, I would say. So, I don't know, to answer your question. I'm not sure, but I think there's hints suggesting that it's at least a new framework that there's hope, right? Because if you're grounded in these structures that start with something that's inherently non-local, inherently non-unitary, that inherently is independent of space-time, and you're finding space-time, or at least properties of space-time being emergent from that, I mean, it's at least one avenue to explore.
Sure.
Okay, thank you.
That seems to me to be exactly right. And I was very interested in your, I'm afraid I really must go back and look again at some of these. I've only seen the kind of popular accounts of it. But this kinematic space that the string theorist, and particularly, I'm sorry, I can never say his name correctly, but Arkady Hamed and his colleagues have been working with. It certainly does seem to be mathematically very, very rich. It's just I hadn't actually glimpsed the idea that it might be in some way, but conceivably, directly foundational but from what you're telling me, you mentioned that there was some connection with Grothendieck's work in the ideas they use, particularly in connection with the possible non-unitarity and non-locality. Can you give me any references for that, or?
Well, let's see. I'd have to think about it more.
Maybe we should correspond about this off off piste, as it were. Yeah, if that's okay with you.
And I'll also mention that from my perspective, I was studying scattering amplitudes. Nima Arkani Hamed is kind of backing out of string theory and diving into the scattering amplitudes community. Like, he kind of gets it that, maybe but it's just that the way to look at string theory and supersymmetry is that it's a toy model. If you look at n=4 super Yang-Mills theory, the scattering amplitudes are way easier. Like, for the LHC, 99% of the computation time needed is not even in the most supersymmetric theories. So really what it is when you start looking at the solutions of physical theories and you start studying solutions of string theory, you start realizing, oh, reality is actually much more complicated than string theory, but no one wants to hear that because string theory is already pretty complicated.
George, we would like you to have the last word.
Yes.
Okay, I'd like to just quickly comment on what Roger said. Cohomology is definitely fundamental, and there is actually a organization of cohomology which is more recent due to Deligne, which I think we can exploit in twistor theory. But also, if you follow, as somebody mentioned earlier, Peter Voigt's blog at all, you'll realize that there's a revolution going on in mathematics, led by Peter Schultz. At the root of it is ideas like Deligne cohomology. And a key ingredient in Schultz's work, not necessarily other people's, is what they call the twistor curve. It's a P1. And it would be very interesting to try to integrate their ideas with ideas that we're familiar with.
I think we should get together, George, if it's okay with you, and perhaps with Roger to I'd be very grateful for at least for an initial reading list on some of this. I have been following Peter Schultz's blog, and I'm certainly aware of just how incredibly deep the ideas from the lean cohomology are, but that they were possibly relevant to this kinematic space that Arkady Hamed and co have been exploring. I hadn't actually heard that suggestion until now, but this strikes me as extremely exciting, and I would love to learn more.
Okay.
Thanks. But in the meantime, unless anybody else has any other comments, Roger, is there anything you wanted to add before we thank George?
No, only me too. Please not to continue many more other things I have to do. So no,
I'm sorry we've taken. Well, no, I'm not going to apologise because I'm sure you enjoyed every moment of this.
Oh, no, it's been great fun. Yes, yes.
It was great fun. It was a very good discussion. It was a wonderful talk. So thank you all, and especially obviously to George.
And thank you. Thank you very much.
Well, I'm very. It was an inspiration that we invited you because this has been one of the most deep going and far-ranging talks and discussions we've had since the beginning of the series. So thank you again, everybody, and we look forward to. It's in 2 weeks' time, isn't it?
Yeah, 1st of November. Andrew Hamilton to talk on geometric algebra and unification.
That's right.
I think the follow-up of Lazenby's talk, I think.
Yes.
Should be very interesting.
So a different perspective, a different angle on possible roads to unification. But this has been an absolutely wonderful talk. Thank you all very much indeed. And hopefully see you in 2 weeks' time.